Okay, so we'll go ahead and get started. If you're still working on the quiz, keep working on it. But if you finished, we open to page 38. And we'll take a look at the calendar together once everybody's done working on the quiz. So we'll start on page 38, and I think that this section will be a welcome reprieve for many of you. This section is quite straightforward. It's just a calculation technique, and it's pretty much just one procedure that's pretty easy to follow. So hopefully this will be a nice break. Anybody know French? Used to? Abby, can you pronounce this guy's name for us? Go ahead, Nikki. Wonderful. Okay, so this is one guy, and that's his entire name. We just call him L'Hopital for short. And let's read a tiny bit about him. So we'll go over to Tiffany. So true story, and Bernoulli is part of a famous family of mathematicians, physicists, scientists. You might have heard of any number of them. You know, L'Hopital paid Bernoulli for his work, and then L'Hopital's only contribution to that textbook was the cover page, which had L'Hopital's name on it. Bernoulli wasn't really able to say anything because he had been paid for his work, and I guess this was technically allowed back then. Once L'Hopital passed away, Bernoulli then came forward and said, hey, all of this is mine. It turns out he was right. Sadly, the name has stuck. It's called L'Hopital's rule, should be Bernoulli's rule. So we'll try number 2 here. There were 2 limits that you guys tackled for the questions of the day. Both of them were the same rational function. What was the only difference between the 2 limits? What was the difference between these 2 limits? That's right, we're just sending x to different things. Otherwise, the fractions are the same. So we're going to try the first limit, which is this x going to 2 business. So we'll do this in a couple of different ways. So first thing we're going to do is we're just going to plug in. Anytime we see a new limit today and any day, first thing you have to do is plug in. So go ahead and plug 2 into the top and separately plug 2 into the bottom. And let's see what we get.
May I borrow 1 or 2 folders?
Sure. What do we get when we plug in? 0 over 0. And I don't know if you guys remember, it's been a while since we have looked at limits together, but 0 over 0, was that a good sign or a bad sign for us? It was a bad sign for us. That means there's more work to do. So 2 techniques. The technique that we had before was to factor the top and the bottom. So this is going to be limit as x approaches 2, and it turns out the top and the bottom factor is going to be a little bit of a pain because of the 3x squared and the 5x squared. But see if you can somehow factor one or both of those pieces. And I think there's a really useful hint. If we went to 0 over 0, then x minus 2 is going to be a factor for both of them. See if you can convince yourself that's true. Anybody have either of them? Okay, so this one down here is a 3x plus 5, and downstairs? 5x. Is it 12 or 13? 5x plus 13. Yeah, we factored them both correctly, but you can see how long it takes to factor. Probably many of us haven't finished factoring yet, but that's a real pain because of the 3 and the 5. So that factoring isn't easy. But once we've got it factored, what can we do? So we cancel, and we have a new limit. And you're going to plug into this new limit, and you're going to get some reasonable number, and that will be the answer. So what do we get when we plug in 2 for these x's? 11 over 23. Good. All right, so that was the old way that we approached this limit problem. 0 over 0. If it's polynomials, you factor. Even if it's really hard to factor, you have a process. So here's the new way. The new way is this thing called L'Hopital's rule. Here's what it says. It says that the limit that we had before is exactly the same as another limit. And the way we create this other limit is by separately taking a derivative of the top and the bottom. So upstairs, I'm going to put the derivative of the top. What's the derivative of 3x squared minus x minus 10? 6x minus 1. That's the derivative downstairs. 10x plus 3. Yes? And now plug in the same x equals 2 into this. What do we get? Same thing. 11 over 23. That's a good question. We had all these limits to take care of before we were able to take derivatives. So we didn't have the derivative tool to help us. But clearly, and I think I hear this in Garrett's tone, the second way is much better for us, right? I mean, it's a lot easier to do that than this. So back when we did this, we didn't have the tool, but now we have it, so we use it. Two things to say about L'Hopital's rule. First, it only applies when you have certain forms as your limit. One of the acceptable forms for L'Hopital's rule is 0 over 0. So anytime you get 0 over 0, you are welcome to do this technique where you take derivatives top and bottom. Second thing, it's not a quotient rule. We're not taking the derivative of this fraction. We are separately treating the numerator and denominator derivatives for each. Okay? All right, so that's that. Let's take a look at the limit on the next page. It looks very similar. What's the only difference? It goes to infinity. Okay, so x is going to infinity. Do you guys remember the technique? It was actually a pre-calculus technique. Okay, so we're looking at the biggest powers because the leading terms are going to be the ones that matter. When x goes to infinity, they dominate everything else. And in this case, Garrett says 3/5. What is he observing about those leading terms before he says 3/5? Yeah, equally dominant. They have the same power. They're both x squared. And so if they're the same, then you just cancel the x's and you get the coefficients. 3/5 is the answer to this. And I'll say that we got 3/5 by kind of waving our hands around. Some very fuzzy math that we did back in pre-calc when we said, okay, so first you can ignore everything but the leading term. I think we're probably convinced, but I mean, if x is 1,000,000, then subtracting 1,000,000 would normally be fairly significant. So that's kind of fuzzy to just say, well, ignore everything except for the leading terms. And then, if we just get the stuff circled in purple, what is the top equal to when you plug in x equals infinity? What does the top thing approach? Infinity. What does the bottom approach? Infinity. So somehow the old rule that you had where if it's the same on top and bottom, it's equal to 1, we're just tossing that out the window. That's kind of weird, right? I mean, how much is x over x? It's 1, and infinity over infinity somehow now is 3/5. So that's kind of strange. So let's try the L'Hopital's rule way. So, or let's say this is equal to limit as x goes to infinity. Again, take a derivative top and bottom separately. So we get the same 6x minus 1 over 10x plus 3. And now what happens to the top when x goes to infinity? What does it approach? Still approaches infinity. How about the bottom? Still approaches infinity. Well, L'Hopital's rule works when you have two things approaching infinity. So what can we do? We do it again, right? Let's just take another derivative. This equals limit as x approaches infinity of, and what's the fraction here? 6 over 10. One more layer of derivatives. And what is that equal to when you take the limit? It's the same 3/5 that we got before.
So it's like, I don't know, I saw a thing a while ago online about how different infinities are different sizes. Like if you picture the infinity that is like all whole integers, picture it's all even numbers. The infinity of the whole integers is very still.
Yeah, there's lots of stuff to say about the levels of infinity, and I think there's some really interesting videos out there. Maybe you can share a link with us. I can email it around or something. For us, I think that we are going to have different infinities in the sense of dominance. Like one thing can go to infinity a lot faster than something else. In my mind, I don't have a connection that I can offer between the counting different kinds of infinities versus the dominance, which is what we're talking about here. But I got to think about it. All right, so which way was easier, the pre-calc way or the calculus way? This one, pre-calc, is pretty easy, right? So why am I offering you something that's longer than the pre-calc way? Well, first, we can get rid of this hand waving. If we buy into this idea of taking derivatives separately, then all right, at least that's on more solid ground. Second, the pre-calc way is only good if it's polynomial over polynomial. But if instead I gave you something like e to the x over 5x squared, okay, there's no pre-calc way anymore. Now we just have to really think about which one dominates the other one. So the pre-calc way is only easy artificially, only if it happens to be some nice polynomial over polynomial. So last thing I want to say is if you are doing something like this on a test or a quiz, I'm going to ask you guys to give me some little symbol that tells me that you have applied L'Hopital's rule. So anytime you're going to do that step where you take derivatives separately, top and bottom, just put an LH right above the equal sign where you take that step. That's not standard notation. It's just something that cues me into what you are doing. So I'm going to do it on the next page as well. So right here, when we took the first derivatives, and then again, when we took the next derivatives, okay? You keep taking derivatives until things don't go to one of these particular forms that we're about to name right here. So Chris, go ahead and read number 3. Okay, so those are the two kinds of things that you are allowed to do L'Hopital's rule on. 0 over 0 was the first thing we saw, and then infinity over infinity was the second thing that we saw. All right, so you keep going until you don't get one of those forms. All right, so turns out whether the infinities are pluses or minuses makes no difference. Any kind of infinity over any kind of infinity, we use this rule. All right, so let's jump down to number 4, and we'll go to Joe. Okay, so let's do a few of them. We're going to start with part A. So this is a limit as x approaches 2 the first thing you do is not L'Hopital's rule. The first thing you do is plug in. So what do we get when we plug x equals 2? We get 0 over 0. That's our indicator that we're allowed to use L'Hopital's rule, so we'll do it. And I'll put a little LH on top. Don't forget to write that limit, and then take the derivatives separately. What do we get upstairs? 2x over 1. The derivative of x minus 2 is just 1 for the 1x. And you have a new limit. Don't apply L'Hopital's rule again. Plug in. What do we get? 4. 4 is the answer. If you decided you were going to use L'Hopital's rule again, what would you get for the derivative upstairs? 2 downstairs, 0. Now it's undefined. It's definitely not 4. Right? So L'Hopital's rule will lead you to a wrong answer if you just apply it willy-nilly. You only get to apply it if you have one of the forms that Chris read, 0 over 0 or infinities over infinities. Let's try part B, and I'm going to remind you, oh, well, first thing to do is what? For any limit, the first thing we do is plug in. So plug in x equals 0. And you get 0 over 0. So L'Hopital's rule is fine, and we're going to use it. But I want to remind you that actually we were able to do this limit before we had L'Hopital's rule. Do you guys remember this famous limit we talked about one day, way back when? Sine of theta over theta as theta goes to 0. You guys remember what that limit was equal to? It was equal to 1. We didn't actually prove it. I just said, hey, it's a famous limit, and it's equal to 1. And if you want to see the proof, see me after class. It takes like 2 minutes. But using that limit, we were able to find the limits like part B. All this says is sine of something over the same thing. That's the goal. Okay, you have no control over the 2x that's inside of the sine function. I can't get in there. But I could make the bottom. What would I like the bottom to be? I'd really like it to be 2x, because then that limit is of the form green. And so what is this limit equal to? It's equal to 1, because it's the green limit, because it's sine of something over exactly the same thing. But I can't go around just multiplying the bottom of a fraction by 2 without multiplying the top of the fraction by 2. Do you guys remember we did these maybe a month ago? So what does this thing approach because of the green? It approaches 1. So what does the whole thing approach? 2. Great, so 2 is the answer. But let's do the L'Hopital way instead. Okay, what's the derivative of sine of 2x? And then don't forget chain rule times the derivative of the stuff. And derivative downstairs is 1. And then go ahead and plug in 0 for your x. What do we get? 2. That's what we said we were going to get before, but a different way to get that number. Okay, let's skip down to part D. So I've gotten kind of weary of plugging in first, so let's just jump to the L'Hopital's rule part. What's the derivative upstairs? E to the x, right? What's the derivative downstairs? 3x squared. And then just plug in. We get e squared over 12. Yes? So what should we have done first? Plugged in. Okay, so let's go back and plug in. When we plug in, we get e squared minus 1 over 2 cubed is 8. Are we allowed to use L'Hopital's rule? No. Does L'Hopital's rule give us the right answer, which is definitely this e squared minus 1 over 8? No. So don't do that. So always plug in first. Okay, A, B, D. Next we're going to I and J on the next page. Okay, so I is this business here with the x over e to the x. When x goes to infinity, what happens upstairs? Infinity. And downstairs? Also infinity. Let's do the pre-calc way before we do the calc way. Which of those infinities is the bigger one? Is e, right? We've just been trained that e dominates everything. So if the infinity on the bottom is dwarfing the infinity upstairs, then what is that fraction approaching? It goes to 0. Okay, so again, that's the pre-calculus, very hand-wavy type argument. Let's see if we can do the calculus version. So we're going to put the LH because we're about to take our derivatives. Derivative upstairs, 1. Downstairs, e to the x. And then we plug in infinity, 1 over infinity, which goes to 0. Okay, just because I'm recording this, I don't want to get in trouble. Technically, we shouldn't be writing 1 over infinity. We should just write 0 is the answer. But we're thinking 1 over infinity.
1 over infinity and 0, are they?
1 over infinity doesn't have meaning. What we're really saying is 1 divided by something very large, and that approaches 0. Okay, any questions on that one? And we're not surprised that it went to 0 because we knew the e was going to win no matter what. This should probably convince you that even if it was like x to 100, and x to the 100 dwarfs e to the x for a while. But eventually e to the x is going to dominate. What's going to happen if I do this L'Hopital's rule business? I'll get 100 x to the 99. What about the bottom? E to the x. And then I'll get, I don't know, 9900 x to the 98. And eventually what's going to happen? Yeah, the e to the x can sit there patiently waiting for you to take 100 derivatives. And eventually the x to the 100th will yield and just become some constant. And we'll get that. Okay, so we've gotten rid of the hand-wavy stuff. E to the x is just going to hang out. It's going to dominate everything because everything else, all the polynomials you can name, will disappear eventually. All right, let's take a look.
So when you take the derivative at the top and the derivative at the bottom, you're looking at the rate at which they're changing and comparing the two.
That's right.
You're dividing them, you're seeing differences.
Yeah,
ratio.
we're looking at the ratio of slopes. That's what we're doing.
That's why you just keep doing it.
Okay, how about J? X is going to 0. What does the plus sign mean? From the right, from the positive side in this case, ln x over cosecant x. First step, plug in. Okay, plugging in here is not as easy as the other ones, but at least it gives us a chance to review the cosecant function. So first thinking about the graph of ln, do you guys remember what it looks like? You draw it in the air. ln x, y equals ln x. Good. So where do I start my graph? Where's the asymptote for this graph? The y-axis. So I start way down here, comes up, that's it. So as x approaches 0 from the right, what happens to ln x? Goes to negative infinity. Everybody see it? X approaches 0 this way, and the y values go to minus infinity. All right, cosecant. Doesn't get very much attention. Cosecant is the reciprocal of which better known trig function? Sine. So the way that I remember what cosecant looks like is to graph the sine function. So the graph of y equals sine x, does it start at the top, middle, or bottom? So sine x starts at the origin and is going which way? It's going up. So I'm just going to graph one of those sine things there. And if I want to graph cosecant, it's actually going to hit the sine curve. One other thing I want to do is go to each of the x-intercepts of the sine curve. Do you know what I'm going to draw for the cosecant graph? Vertical asymptotes. Because cosecant, remember, is 1 over sine. And if I'm trying to do 1 over 0, it's undefined. It's vertical asymptotes at those spots. And now that we've got our shell up here, the graph of cosecant is really quite nice. It's just going to get close to the asymptotes, and it's going to bounce off the sine function. And then you just get those repeating cups alternating up and down.
Is that the same for secant?
Same shape for secant. Essentially you are, but ln of 0 is undefined. It doesn't just stop the problem. No, I mean, because ln approaches, so infinities are something that we can handle. And it turns out that ln being undefined really means that it's approaching minus infinity in this case. So the graph is what I need to do to figure out what it's doing. Yeah, and then that's it. Okay, so what about x going to 0 from the right for the cosecant x? What happens to the purple function? Goes to positive infinity. Everybody see it? As we approach 0 from the right, we get all these points, which we ignore. We get these points, and eventually head over there to infinity. So this approaches minus infinity over infinity. That right there is one of our allowable forms. That's one of the indeterminate forms. Any infinity over any infinity. Plus minus doesn't matter. So that means we get to take derivatives. So I'm going to squeeze this one up here. Equals L'Hopital's rule. Every time we're writing this limit part, and then go ahead and take a derivative, top and bottom separately. Let's see how many of you remember the derivative of cosecant. Okay, so the derivative upstairs is 1 over x. That's the more memorable one. Derivative downstairs. Good. Okay, so we have this new limit. It looks worse than the original limit. If I plug 0 in for x, then the top approaches what? It's like 1 over 0. It does become undefined, but I don't want us to say that word. I want something else. It doesn't approach 0. 1 over 0 approaching infinity. That's what the top is doing. And then cosecant of 0, we already figured out. What is that approaching? That's approaching positive infinity times cotan. All right, I'm already overwhelmed. I don't even want to know what it does. It feels like if I have to take another derivative, it's going to get way worse than it currently is, and that doesn't seem to be making progress for us. So how about we just put another equals here. And I'm not going to put an LH because I'm not doing L'Hopital's rule. I'm just going to rewrite this thing. So I'm going to try to clean this up so I just have one fraction. Is that x in the top or the bottom of my one fraction? It's in the bottom. If you feel like it, you can multiply up here by x to cancel that one, and down here by x. So x is in the bottom. So we'll put our x downstairs. And then I have a cosecant downstairs. What is that if I put it upstairs? That's really sine x. I'll bring the negative up. It doesn't matter where you put the negative. What is cotangent on the bottom? when I bring it up, it's really tangent. Okay, so at least I've got functions that I'm more comfortable with now. So that makes me feel better. And now I'll go ahead and plug in. So upstairs, I got sine of 0 is 0. Tangent of 0 is 0. I don't like where this is going. What do we get on the bottom? 0. Okay, so we get 0 over 0. So what do we do? Now the derivative. But before you feel like you're caught in some infinite loop, what is the derivative of the bottom? Is 1. The infinite loop is about to end, right? There's hope on the horizon. It's not going to go past this next one, but we got to do the next one. What rule upstairs? Product rule. Go ahead and do the product rule upstairs, separately the derivative downstairs, and then plug in. Okay, so we use our product rule. We get this big mess upstairs, and then just 1 downstairs. And now when we plug in, good things happen. I think it's a minus, I think. But the product rule normally has a plus, but there's a negative that's going to come in. That negative is going to change all the signs to minus. Okay, so we're plugging in sine of 0 is 0. Secant of 0, probably tougher to do in your mind, but secant is 1 over cosine. So that's really talking about cosine of 0. How much is cosine of 0? 1. Now it's 1 over that number, which is still 1. And then it's squared is really 1. Okay, and then minus. So the first thing is nothing. Minus, how much is tangent of 0? That's 0. Cosine of 0 is 1. So the whole thing is a 0 minus a 0. 0 over 1. All right. Okay, any questions on L'Hopital's rule? So it's a fairly straightforward technique. The first thing you always do when you see a limit is plug in. If it happens to be one of the 2 acceptable things, 0 over 0 or infinities over infinities, then we get to use L'Hopital's rule, which says take derivatives separately. Sometimes that's quite easy, other times it's quite involved, but still it's just separate derivatives, and then plug in again. And the only new thing from this problem is that sometimes you want to clean the thing up before you try L'Hopital's rule the second time. And so in this case, I wasn't thrilled because if I took another derivative, that would get worse. This would get really worse. And I just didn't like the way that it looked. So I was able to clean it up and just make one kind of more comfortable looking fraction there, and then L'Hopital's rule. You should, but the difficulty is that that cleaning up this fraction ended us taking this guy right here, the 1 over x, and making it just an x, and then that x had a derivative that was just 1. But if you take the derivative of 1 over x as it is, what do you get? Negative 1 over x squared. So now all of a sudden, there's actually more x's downstairs, 1 over x squared. And so you're heading in the wrong direction. It'd still be equivalent, and you can still eventually clean it up, but I think it's not gonna necessarily take you in a straight line to this answer.
So you're going to have to be a lot more work.
Yeah, a lot more work, and it will keep getting worse until you recognize, oh, I really need to get that x downstairs so that you're not taking a derivative of 1 over x, which gets worse, but instead you're taking a derivative of just x, which gets better. Good question. Okay, so let's go down here to number 7. 7 talks about several other indeterminate forms, things that we can't know what they approach. In the examples that we've seen today, the first one we did, we had this fraction that was going to 0 over 0. It turned out it was really going to 11 over 23. So that should convince you, that random looking number should convince you that if you get 0 over 0, the answer could really be anything, right? Could be 1, could be infinity, could be 0, could be 11/23. It really could be anything. And then the same kind of thing for this infinities business. This part here, it looked like we were getting infinity over infinity, and it turned out the answer was 3/5. So again, you should be convinced infinity over infinity really could just turn into anything over here. And then there are some other kinds of places where we have competing forces, and that's this list down here. 0 times infinity. Suppose that it wasn't 0. Suppose that it was 0.1. What is that times infinity? That's infinity, right? What if instead it was 0 times something that I'll say is close to infinity? Anybody know the name of the number 10 to the 100? That's a googol. Good. 1 with 100 zeros. So how much is 0 times a googol? It's 0. So what if it was like a 0.1 and then times 10 to the 1,000? And you can see these two things trying to compete with each other, right? The 0 wants to stay at 0. The infinity wants to pull it up to infinity. And so, you know, who wins? I don't know. Depends on what the thing is. The answer could be anything. Could be 11/23. It just really depends. Another case of conflicting forces here, competing forces, is infinity minus infinity. What's it equal to? Well, if I just follow my normal algebra rules, what's it equal to? 0. But it really could be anything. It just depends on how the infinities relate to each other. What levels are these infinities? 0 to the 0. How much is 0 to anything? 0 to anything is 0. How much is x to the 0? Is 1. So how much is 0 to the 0? I don't know. You've been lied to, right? They can't both be true, right? I can't tell you simultaneously that 0 to anything is 0 and x to the 0 is 1 because I've got conflicting things happening when x is 0, right? If you type 0 to the 0 on the calculator, maybe that will shed some light on this. Yeah, I was hoping it would shed some light on it, but it didn't. So again, conflicting stuff. Infinity to the 0, conflicting stuff. 1 to the infinity is conflicting stuff. Yes. No. Let's go to the next page. Right. All right. So we got those conflicting forces. Here are some that aren't conflicting forces. What do you think for 0 over infinity? It's like super 0, right? I mean, like in this case, both parts are trying to get you to 0, and they'll both win. How about 1 to the 0? Okay, that's 1. 0 to the first? That's 0. That's fine. Why do I have 0 to the infinity in that list? 0 to the infinity. Is it just 0? Yeah, it's 0. Yeah, because the 0 isn't really a 0. It's something very close to 0. But if you raise that to lots of powers, it's going to get even closer to 0. It keeps trying to get closer and closer to 0, right? 0.1 times 0.1 times 0.1 times 0.1. Just like point, and then a bunch of zeros with a 1. Okay, so there's a whole slew of indeterminate forms we saw on the previous page. There's a slew of things that look promising, but they're not indeterminate at all. They're all, both parts are working together. But the only ones you're responsible for are the 3 in this list. So 0 over 0 we've seen. Infinities over infinity we've seen. And we're going to look at one example right now of a 0 times infinity. So those are the only 3 I'm going to ask you about. So let's take a look at part A here. The limit as x approaches 0 from the right of x times ln of x. So first we plug in. What do we get for the x? 0 times. How about ln of 0 from the right? It's the negative infinity that we saw before because ln goes down to the y-axis. So we've seen that. And I'm hoping you can kind of see these as 2 conflicting forces. 0 times anything wants to stay at 0, but minus infinity times anything wants to pull you down to minus infinity. So we got to find out where they meet. Okay, you cannot use L'Hopital's rule unless you have a fraction. I say again, you cannot use L'Hopital's rule unless you have a fraction. So don't just take derivatives of both of those terms. What you need to do is make a fraction. So here's how we're going to make a fraction. You're going to take either x or ln of x and shove it downstairs. So here are your two choices. You could either keep the x up here and put the ln x down there by putting it as a 1 over. Who would buy that's the same as having the original. Or you could keep which one upstairs? ln x, and then what goes downstairs? 1 over x. Which one seems better for us? Maybe the second one. I know my derivative of 1 over x. 1 over ln of x is going to be kind of a uglier derivative, I feel. So let's do the second one. And in doing the homework, if you choose poorly, you'll know because the next derivative layer will look a lot worse than the original. Okay, again, we're just going to plug in. What do we get for ln 0 from the right? That's still the minus infinity. But downstairs now, we've changed things. 0 from the right, 1 over 0. It is undefined. Josiah? Infinity. Yeah, if you're feeling undefined, the answer is undoubtedly infinity or minus infinity. Like those are the two choices. You just have to pick the one that's right. How do I know it goes to positive infinity? Because we're going to 0 from the right-hand side, plugging in only positive numbers. Okay, is that one of the acceptable L'Hopital forms? It is. So take derivatives separately. Go ahead and write that little LH on top. What's the derivative upstairs? 1 over x divided by, what's the derivative downstairs? Negative 1 over x squared. Now you're welcome to just plug 0 in, but if you do, you're just going to get more infinities over infinities. So what we need to do instead is clean this thing up. So this equals limit x goes to 0 from the right. Make that one fraction for me. What is it? Good. 1 over is this universal, flipping type thing, right? Move it to the other spot. So the x squared is really upstairs, and the x is really downstairs. That negative can go anywhere. So when I cancel those x's, cancel the x's. Don't plug in 0. Have an opportunity to cancel. Do it. And now plug in 0, and what do we get? We get 0. Okay, and I will, you said satisfying or unsatisfying to get the 0? Unsatisfying, sorry. It's a long way to go for a little bit of information, but let's at least give you the information that we found here. The original thing, I'm trying not to block this for people that are copying. The original thing was this x ln of x. I'm going to graph that function. F of x equals x times ln of x. Before I hit the enter key, we just got some information about this function. As x approaches 0 from the right, what does the function do? It goes to 0. So what point is, I'm not going to say on the curve, but what point is basically on the curve? The origin. Because when x is 0, turns out the function is also 0. So let's take a look here. I'm graphing this function, we hit enter, and lo and behold, right there near the origin, you can see the function approaches 0, 0. Okay? And it's kind of strange because, you know, this is two different functions that I'm thinking about. G of x is just that line. But the other function that I was thinking about was ln of x, which has the vertical asymptote. And so how, you know, like what happens for those two functions? Let's bring this down a little bit. So I've got these two functions and I'm just multiplying them together. And so the question is, you know, what happens? X and ln of x are both going to infinity to the right. So I believe when I multiply them together that the whole thing will go up to infinity. But what about when the ln wants to go to minus infinity and the x wants to just go to 0? The 1, the 0, 1, the x 1. Right? The ln wanted to pull this thing down to minus infinity. It won for a little while. You can see it dip down here for a little while. But then eventually the x got strong enough to pull it back up to the origin. Okay, so there is one other example I want to look at, but before we do, let's just take our look at the calendar here and make sure we all know what's happening. So we just had quiz number 8. Project 7 is also due. I know it's a tough project. If you haven't finished it, turn it in on Monday. It's a 5-point penalty. If you can get more than 5 points of credit on this thing by looking at it for another 2 days over the weekend, then do it. Monday is our review day for the test. Wednesday is the test. I'm going to plan on coming in here on Monday just like we normally do, and we'll just talk very generally about the test. Essentially, it's on all this material between test 2 and test 3, so you know exactly which sections it's on. And I want to point out that if you go to the next page, this is page 42, you'll find the familiar looking study guide with a list of the things I'd like you to be able to do to be prepared for Wednesday's test. There's a bunch of problems that were not assigned for homework that you can try. You can look at old homework assignments. You can look at old quizzes. I'll give you this quiz back on Monday. And then on the next page, more familiar looking sample test problems. And again, I've got videos for all these things, and you find them in the usual way. You just need to know how to find them. So for example, if you wanted to look at problem 2, you type in exactly that phrase with no spaces. So maybe make a note of it if you're ever having trouble finding my videos. 201 sample test 3, problem 2. And if you hit enter on that, it pulls up some advertisements, then it pulls up my playlist. There's the actual video of me going through problem number 2. Here's the full playlist. And then you can just kind of pick which ones you want to look at, okay? All right, problem number 3 has no views yet. It's feeling a little bit left out. So give it a shot. Try problem 3 over the weekend and check out the video if you get stuck. Okay, so. No, there's test is Wednesday. Yeah. One other announcement. So I know that I've completely confused you all in terms of when the final exam is, and I don't know why I wasn't able to read that thing, but the final exam is officially the same as we've been saying for weeks now. It's December the 20th. That is a Thursday, which is quite surprising. For you guys, the exam is between 8 and 10:30, right here in this room. That said, do you not have you don't have an exam? Like you might have an exam at 10:30. So, okay, so inspired by Ted's magic, so there is another day on which we could do the exam. It's the exact same times. People are welcome to come to my 10:30. I'm just going to be sitting in this room for like 7 miserable hours. But you're welcome to come to the 10:30, but if too many of you come to the 10:30, then we're not going to have enough room in here. So I'm probably going to ask for like a head count as we get closer, just to make sure that we have enough seats for everybody. That said, so officially our exam is that Thursday. It turns out that we could move it up one day to Wednesday the 19th, exactly the same times, and I can guarantee you that you do not have a conflict with Wednesday the 19th at 8 o'clock. I know this to be true. So there's pros and cons. If we move it to Wednesday, then maybe your winter break starts a day earlier, but you have a day less to study. And so I need you guys to think about weighing that, okay? So just think about it over the weekend. I will ask you again on Monday. I'm not going to have some people take it Wednesday and some people take it Thursday. One miserable 7-hour day in this room is enough for me. So, so just think about it. Your choices are either the Thursday or the Wednesday. I'll come back to you on Monday about that. Okay, and so the last thing is this problem right here. Okay, 1 plus 1 over x to the x. I'm going to fly through this one. This is not, here you can read it here. It says you won't be tested on the technique we're about to see, so don't write it down. We're just going to go through this as quick as we possibly can. I've got this limit right here. If you approach infinity, this guy right here is like 1 plus nothing. And then I'm raising it to the infinity. And it turns out 1 to the infinity is one of those competing forces examples. So what we're going to do is we're going to give a name to this thing here. 1 plus 1 over x to the x. Just going to call it y. And then what I'm going to do is take the ln of both sides, natural log of both sides. And we know that natural logs on a power allow you to bring the power down in front. Agree? Okay. And then what I'm going to do is I'm going to send x to infinity on this whole thing. Except I can't do L'Hopital's rule unless we have fraction. So then I'm going to rewrite this guy as a fraction. It should look very similar to the one we did over there. Downstairs, I need to put that x, so it becomes 1 over x. Turns out this will be a L'Hopital's rule. It's going to be, if x goes to infinity, this is going to be a 0 over 0. Fine. So we take derivatives separately. So I'll put it here with an LH on top. Derivative of ln is 1 over the stuff times the derivative of the stuff. What's the derivative of the stuff? Negative 1 over x squared. That's the derivative of the ln. Divide by the derivative of the 1 over x is also negative 1 over x squared. What nice thing happens? Cancel that part. Again, we were sending x to infinity. If x goes to infinity, what happens to this guy? Small, 0. So what happens to the whole fraction? It goes to 1. So what we've just figured out, and I know I'm 10 seconds over, apologies. We've just figured out that ln of y is going to 1. This whole thing that we called ln of y is going to 1. So if you hit both sides with an e, then what does y go to? You can see it goes to e to the first. If ln of y is the same as 1, then y is the same as e. And y was the thing that we gave the name to originally. This guy right here is our old friend e. You can't bring the x inside the ln. Oh, you could do that, but when you take the derivative upstairs, you have to use the product rule then, right? Which I think would make it messy. I think. I haven't looked at it. I'll give it a shot. Okay, sorry we went late today. We'll see you guys on Monday. Have a great weekend.